In this video, I'm finally going to start talking about point group symmetries, sort of getting down to what we're actually going to be talking about here. In a way, the preceding videos to this one in this group theory playlist were kind of preamble to this. And so now I'm actually going to talk in this video about the point group symmetries, so the various types of symmetry that we can have. Then in the next few videos after this, I'm actually going to go through each of the point groups, at least up to octahedral. I'm not going to really talk about the dodecahedral and the icosahedral because, I mean, those are, very high order, and they don't have as much application to the sort of chemistry that I'm going to be talking about here. But so that kind of brings me to the other thing I wanted to say. I'm going to be using a lot of chemistry to show the point groups and the symmetries and stuff like that, because that's kind of the motivation for this video, but also they're just really nice for visualizing these different symmetries and things like that. And so this is going to be, almost half a chemistry, half a math playlist from here on out, or at least in the next few videos anyway. But anyway, with that all out of the way, so once again, this is our C3V symmetry group here that we've been using as an example. So this is the C3V. And we see the different symmetry operations that it has. So we have obviously the identity operation. Then we have this rotation counterclockwise by, in this case for the C3V, it's 120 degrees. We have this, which is the clockwise rotation, 120 degrees, such that doing one and then the other gives us the identity element. Then we have each of these different reflections here across a plane that would be sort of sticking in and out of the page right here. And so those are some of the symmetry operations that we will be thinking about. If we look at something with a little bit higher order symmetry here, we can actually see that you can end up having sort of multiple different sort of rotations and reflections and stuff like that. So we have this one up here, which is C6. So this is a hexagon. You can see you could, move this point right here over to here. So that's 1, then 2, then 3, then 4, then 5, then 6 to get back there. And so that will be our principal axis on this one, because it has the highest order of rotational symmetry here, where then we can see there are these other ones here that are C2, then the C2 prime here, which is kind of in between two different C2s. But we see that we could sort of, take this point here, and sort of flip it over until it ends up at that point there, where this one here would this one here would sort of end up, yeah, this one would actually not there, so it would actually end up, if we are flipping across this axis right here, then this one will end up here, this one will end up here, and so those two will switch sides and these two will switch sides, and so we have this twofold axis here. Then we see we have these two different types of reflections, and so we have this sigma v reflection. So remember, in our C3V we had that 3 and the v. The 3 was telling us the sort of highest order axis of rotation, and the v was telling us that we had this reflection here. And so we see that that a plane sort of sticking up this way, reflecting sort of across this right here, would sort of reflect that side to this side and that side to this side. And so we can see all these different sorts of symmetries here. And then of course there is the sigma h, which is actually reflecting, so with the thick here is sort of projecting out of the page. So this would actually be a reflection sort of up and down. And so those are the three types of reflections. These are the two types of rotations that we will sort of run into, is these sort of higher order ones and then these lower order ones. And so everything up through, so like our C and C, well, I'll talk about that in the next video, but there are the tetrahedral and octahedral that will actually have more than one sort of principal axis, but I'll talk about that when I get there. So once again, so the principal axis, the axis of rotation with the highest order, it's sort of conventionally put as the z-axis, so you'll often see it sort of sticking up here, or if you're sort of looking at this without the sort of projecting into the page, so it would be something like this. And so you'd usually have the z-axis sort of being right in the middle, sort of sticking straight in and out of the page. And so, so it's just convention to put it as the z-axis, and it kind of makes the math easier. So all other rotation axes must be of lower order and perpendicular to the principal axis. So you see this principal axis here is sticking up and down, where each of these lower order ones are sort of, well, they're perpendicular to it. They're normal to it or orthogonal to it, or however you want to put it. Yeah, those have to be perpendicular and they will be lower order. And then actually we'll see here, until we get to those tetrahedral and octahedral, they are restricted to being a C2 axis. You don't get any higher than that in sort of the sort of rotational groups, and then the d-rotational groups. But anyway, so plane of symmetry. So the planes of symmetry are planes about which both sides are mirror images, and they must be either perpendicular to the principal axis or along the principal axis. And so we see it's actually these sigma h's that will always be perpendicular to the principal axis, where these sigma v's and sigma d's, sort of have a plane that kind of runs, that sort of splits that principal axis sort of right in half along the entire length of the thing. And so these are the sort of different kinds of symmetry elements we have. So we have the Cn, which are the rotations, and so that is some rotation 2 pi radians over n, or you could think about it as 360 degrees over n. We have these sigma v reflections, where we're just sort of taking this side and reflecting it over here. So these pluses and crosses are telling us that it's sort of something sticking up out of the page, where when you see these circles, it's telling us something sticking down into the page. And so we see this here preserves the sort of out of the page. We're reflecting sort of, this side here. So if we had, some letter A here, it would end up looking like that on this side. And so that's how that mirror image is happening. Then we have this reflection plane, which is sort of, the plane of the screen here. And so we see that we have this plus here, and then when we reflect it, it just becomes a circle, because something sticking out of the screen is reflected so that it's sticking into the screen. And then we have these C2s here, and so I put a prime here. I'll talk about that here in just a second, but these other C2s, so we see that we're rotating across this here, where on this one, this sort of black circle here is like the axis sticking in and out of the screen, whereas if we had that sort of down here, then we are actually just rotating this axis over 180 degrees, and that's why it's the C2, because C2 is 360 degrees divided by 2 is 180 degrees. 2 pi divided by 2 is pi radians. Then we have these sigma d's, which are like this, where if this is a a sigma v here, and this is a sigma v here, then the sigma d is sort of right in between those. And well, that's why the d is there for either diagonal or dihedral, whichever one is easier for you to remember. Then we have these SN, which are the improper rotations. And so what we do is we rotate it by some amount. So you see this goes up to here, and then we reflect it. We actually do a sigma h. And so a an improper rotation is actually a rotation of some kind, and then a sigma h. So a sigma h, and I guess these ones would actually be commutative here. So we could actually do cn and then sigma h. But anyway, so you rotate by some amount, so some cn amount, and then you reflect it with a sigma h, and that puts it into the screen. And we'll actually see that s sub 2 is just an inversion, and so that's actually where the inversion comes from. All right, so the C sub n operations, so we use those to denote the principal axis. Then we use this where the j in the upper part here, where j equals 1, 2, 3, all the way up to n minus 1 for all other axes. And so that's how you'll often see the other axes denoted that way. So you'll see it like C2, 1, and then C2, 2, and things like that. So here we look at some of these rotations. So we have the C2, and that is just a rotation of 180 degrees. And so if you do it twice, you get back to where you were. So then our C3 here is rotating 120 degrees. So, this hydrogen atom here moves down to here. So that's 1, then 2, then 3, just like with our C3V above with the triangle. And actually we'll find out that ammonia is C3V. And then we can have the C4, which is just a 90-degree rotation, because we have 360 divided by 2 is equal to 180. We have 360 divided by 3 is equal to 120. And we have 360 divided by 4 is equal to 90. And so that's what these sort of numbers here actually mean. And so yeah, the symmetry element is a line going into the paper. So sort of sticking in and out of our screen here. So those are some of the rotations. So reflections perpendicular to the principal axis are denoted with the sigma h. All the other reflection planes are denoted with a sigma v or a sigma d. So the sigma v and d reflection planes contain the principal axis. So the sigma v denotes the class of the sigma L, with the v meaning vertical. And so you'll sometimes see it written with an L, sometimes, or with numbers and sort of a superscript parentheses there. Sometimes you'll see it with primes, and usually when you see it with the actual primes or the explicit numbers up there, they will drop the V for it, and you'll just sort of know from context that it has that single number up there or a prime of some order, and that just tells you that it's V. Where the sigma D is one that's between two sigma V's, where the D can mean either dihedral or diagonal. They're often denoted with two numbers in the parentheses, in the superscript parentheses, with the I and J being the two sigma V. I put axes here, but that should actually be planes between which the sigma d lie. And again, because with the context of it having two numbers up there, the d will often be dropped in the literature. So in my next video, I actually kept the v and d subscripts with these just to kind of help tell them apart, but just kind of as a forewarning, in most of the literature you see on this, they actually drop the V and D, and you just pick up whether it has one or two numbers in the sort of superscript parentheses, that is either a V or a D. So the presence of a sigma D tells us the object has a higher order symmetry. So once again, the sigma H denotes a reflection perpendicular or normal to the principal axis. So we can see some of the reflection planes here. So this has a C4 principal axis. So we see this sigma V here and this sigma V here both contain the principal axis, and those are the verticals, where we have the sigma H here, which is perpendicular to it and would, sort of take a point up here and reflect it down to a point down here, and sort of vice versa. And then we have these sigma Ds here, and so you can see that this happens when we actually uh, are going sort of between each of these sigma V's on here. We still are showing the sigma H. And so, it depends on whether we have sort of this square or rhomboid sort of figure that these sigma D's and sigma V's sort of start making a difference. And so that's why I put a square and rhombus here to show that, the angles and stuff like that become different when we sort of stretch it into this rhomboid figure. So here again are just some of the different reflection planes. So our sigma V here, so it's taking this point right here and reflecting it so that it's that point on this water molecule here. Then we have this other sigma V, which this put a little prime here, but you could have this be, you could have this one be sort of sigma V1 and this one sigma V2 here. We see that this is just sort of reflecting the sort of, back of that molecule there with the front of it there, and so that this atom actually stays the same with that atom there. We can look over here with something with a little bit higher symmetry. So we have these the sigma V here. There'd be another sigma V over here, but we see we have this C2. We have this C2. The one that's sticking in and out of the screen is our principal, so that's the C4, and we have these sigma Ds between the different sigma V's, and the sigma H would be sort of this blue glass pane looking thing here, which would reflect sort of the thing sticking out of the page into the page and the thing into the page out of the page. And so those, once again, are the different reflections. And so the SN, as I said, is a rotation and a reflection sort of perpendicular to that principal axis. And so neither of them have to actually exist, or I mean, they exist kind of, but they don't have to exist as sort of independent symmetry operations. So here we see the case of an S4, and this is actually with a methane atom right here, or methane molecule rather. And so we see that here we're taking this H2 here and we're rotating it. We're doing a C4 so that it ends up now right here. And then we do this sigma H, which sort of takes this and reflects it down to there. So now it is down there. And we're doing the same thing with all the other ones. And so we end up with something that has, something up here and something up here, so it looks the same at all of these points here, and so that's why it is a symmetry operation. So you can see that this is just doing a C2 here, which would just be sort of taking this and reflecting or rotating it over there. So we can actually take this one then and do another one of these S4s where we rotate it by 90 degrees and then reflect through the plane, and so we end up back here again. And so that is saying essentially that S4 S4 is equal to the identity element. So we can look at S6 here. So if we are sort of looking, if we're sort of, our eye is right here, looking down this molecule this way, so we see we have these sort of solid black bars are sort of sticking out of the screen at like a 45-degree angle, where these dotted ones are sticking into the screen at a 45-degree angle, and we're sort of looking down it so that there is a bond back here. So this is actually sort of two atoms, carbon atoms stacked on top of each other. But what we see here is that we have this HA, and we sort of twist that by a C6 rotation so that it ends up over here. Then we see we do this sigma H sort of on a plane that would be sort of, right here. So we're sort of reflecting it across that right there, so that this HA with the solid bar becomes an HA with this dotted bar right here. And so that is just the same as doing the S6 right there. And we can actually see that the C6 and the sigma H are not independent operations themselves, because when we move this down, this C6 like this, we end up with something that looks different here, where now this sort of top looking one is now sticking back, where this one is sticking forward, where here it was back right there and forward right there. Or if we did a sigma H, we would sort of end up with the same thing. But both of them together, we end up getting something that looks, that looks just like what we started with here. So these H atoms sort of change position, but if you didn't have those labeled, you wouldn't be able to tell the difference between those two images. So that is an S6 operation there. And so this is just sort of looking at some of these operations again. So this is looking at that sort of six-sided figure again. So we have the C6. We have our principal axis sticking in and out of the paper. So we have this sigma H, which is just reflecting the top and bottom. So this is showing an eye as well, because we could sort of take each of these and sort of, change places with each of them all at once, and that would be an inversion, which is the same as an S2. So that's the same as an S2. Then we see we have these these C2s rather on all these different axes here. We have our sigma V's going down this way, and then these sigma D's, which would go between each of these sigma V's here. So another thing, if you're looking into the literature on this, you'll encounter something that looks kind of like this, which is showing all the different sort of symmetry operations. And so the C1, so we're just taking this point here, and so you have to sort of do a 360-degree turn to get it back where it was. So 360 divided by the 1 is 1. So this one is a C2, but we're actually rotating instead of around in a circle like this. It's actually rotating sort of around that axis right there. So it's actually rotating around that axis right there. Then we have our C3, which is rotating around an axis sticking in and out of the page, where we have 1, then 2, then 3, like that. C4, 1, 2, 3, 4, so on and so forth. Then we have these C with inversions here, where we see if we rotated this 180 degrees and then did a sigma H, that it would give us back what we had before, where the circle again is sort of something sticking into the page. Here they're using a dot for something sticking out of the page. We have our C2H here, which so this one once again would have that we have an axis here, which can then sort of flip it that way, and we have a sigma, we have a sigma h, which is why these have an h, because if you spun this 180 degrees and then did a sigma h, you would end up with the same thing. Then we have our d's here, and we'll actually see in the next video that the d is the same as a c, except it has additional c2 axes on it. And so we can see here that it has a C2 right here, and it has a C2 right here, where we can do a C2 that way, or we can do a C2 that way, and you can also see that there is a C2 going sort of around that way, and so that's why it's a D2, where this is a D3 because it has these different C2 axes, one there, and one there. Then it has this C3 axis going around this way, and then so on for D4, D6. So then our C2V, which now is a principal axis, the C2, but then the V tells us that we have a V reflection, where we see this one, we can rotate it this way and get back to the same thing, or we can reflect across a plane here or across a plane here and get back the same thing. And so then our C3V, which we've been talking about a lot, C4V, so on and so forth. So yeah, I'm not going to talk about these sort of octahedrals yet. I think these figures are actually sort of more confusing than enlightening. So in a couple videos, I'll get to the octahedrals and tetrahedrals and sort of look at those with, like molecules and things like that. That'll be a little bit more enlightening, I think. So then we have our D3Ds here and our D2Hs, where these D3Ds, so the D, once again, has extra C2 axes. Then the D tells us that we have some sigma D reflections. The D2H, it's D, so it has extra C2 axes. Then the H tells us that it has sigma H reflections, and so on. So like I said, if you look in the literature, you'll find tables that look like this quite often that sort of go through all of the symmetry operations. But anyway, that was it for this video. Like I said, in the next video, I'm going to talk a bit more about these C, the S, and the D types of what are called axial point groups. And they're called axial because they have a principal axis, where then after that, the next video will talk about the tetrahedral and octahedral, which don't have a single principal axis, and so those are sort of higher symmetry sort of groups. But anyway, I hope you found this video helpful, and I will see you in the next one.